The question is, what are key equations for calculating the deformation of an axially loaded 1D rod? We will consider the case of a constant strain in this video. Generally, these are the four major steps. Step 1, we calculate the axial load along the rod. Step 2, we calculate the corresponding axial stress sigma along the rod. Step 3, we use Hooke's law, sigma equals E times epsilon, to determine the axial strain along the rod. And finally, we integrate the strain displacement relation epsilon equal du over dx to determine the displacement u at any point on the rod. This task is particularly simple when you have a strain that is constant along the rod. In that case, strain is simply equal to u divided by L naught, where u is the displacement at the end of the rod, L naught is the initial length of the rod. The specific theories and the equations we use depend on the problem. And here we will consider these four categories of problems. The first broader type would be statically determinate problems. If you recall, these are problems where the equilibrium equations alone would be adequate to calculate the axial load along the rod. In this type, we'll consider two subcategories: problems with constant strain and problems with variable strain. Our second major type would be statically indeterminate problems. So these are problems where the equilibrium equations alone will not be sufficient to solve the problem. We're going to have to use a displacement compatible condition or condition in order to solve these problems. In this type, we'll restrict our discussion to problems with constant strains. In this second type, we'll consider two categories of problems: problems involving mechanical restraints and problems involving thermal effects. Just to keep these videos short, in this particular video, I will only consider the first categories, which is statically determinate problems involving constant strains. This is an example of a problem that falls within this category. We have a 1D rod involving three segments, each having different diameters. The rod is fixed at point A and subjected to some axial loads like 25 kilonewton at point B, 12 kilonewton at point C, and 3 kilonewton at point D. As we indicated before, our first step would be to evaluate the axial force along the rod. Since we have these point loads acting at certain points along the rod, the axial force is going to be different in different segments. In statics, we learned to find internal forces in all kinds of problems, right? Like problems involving beams where the internal forces will consist of bending moment, shear force, and the axial force. Members of trusses where the internal force will be axial force, and so on, right? So what's the method we used? Well, we section the member at the point where we are interested in calculating the internal forces, right? So we do the same thing here. So if I'm interested in finding the internal force, internal axial force within segment number 3, I will come in here and section it like this, right? So here is what we would do. Section the rod at an arbitrary point between C and D, separate the rod into two parts, the left side and the right side, and consider one of the two sides in evaluating the internal force NCD. And in this particular example, I'm using the right side and using the force equilibrium equation in the horizontal direction in order to find this internal force NCD. So NCD works out to be minus 3 kilonewton in this particular example. Let me point out a couple of fundamental things here. Firstly, the value of the axial force NCD is independent of the point of sectioning. I could have sectioned it at any point between C and D, over here, over here, over here, over here, anywhere, right? I would have ended up with the same value for NCD, right? So what does that mean? That means NCD is constant within the segment from C to D. If the internal force is constant, we know the internal stress is going to be constant, right? And then the internal strain is going to be constant in turn. That is because the Hooke's law relates the stress to strain, right? If the stress is constant, strain is also going to be constant. So that's why we put this problem in category 1, the category involving constant strain. But we do note that the internal force is going to be different in different segments, and therefore the internal stresses are going to be different in different segments, and therefore internal strains are also going to be different in different segments. In other words, strains do vary from segment to segment, but within a given segment, strain is a constant. The second important point to note here is that we only had to use the equilibrium equation in the horizontal direction in order to find NCD, right? And that's why this problem is a statically determinate problem. Our second step is to evaluate the axial stress within each segment. This is fairly straightforward. All you have to do is to take the axial force and divide that by the corresponding cross-sectional area of that particular segment. Like, for example, sigma within segment AB would be axial force NAB divided by the cross-sectional area little a AB. Our third step is to find the axial strain within each segment. And here we use Hooke's law, which says sigma equals E times epsilon, and therefore epsilon is sigma divided by E, right? Now we apply this equation to each of the three segments and express the corresponding strains. For example, strain epsilon in segment AB equals axial force NAB divided by the Young's modulus EAB divided by the cross-sectional area little a AB. Our final step is to go ahead and find the displacements. Let's start with something simple first. We have a rod with one segment. The strain within the segment is constant and is given by this equation right here, N over EA. N here is the axial force, E is the Young's modulus, and little a is the cross-sectional area of the rod. Say the rod is fixed at this point, and the initial length of the rod is L0. When the rod is subjected to the axial force N, there's going to be a displacement at the right end of the rod. Let's call that as little u. Since we have a constant strain within the rod, epsilon is also given by little u divided by L0. Remember the definition of the strain, right? Displacement divided by the initial length, right? Now rearranging this equation, we get this expression for the displacement u. U equals n times L0 divided by E times A. So if I have a rod with a single segment, this simple equation will allow me to calculate the displacement at the end of the rod. So now how do we extend this analysis to a rod with multiple segments? We can extend this easily to a rod with multiple segments if we make this one key observation, which is point B moves by a distance u given by this equation only because point A is fixed. But supposing, say, point A also moves to the right by a certain displacement, what is going to be the movement of point B? Well, it's going to be this displacement little u plus whatever the movement of point A is, right? What if point A moves to the left? Well, then the displacement of point B to the right is going to be little u minus the displacement by which point A moves to the left, right? To sum it up, this little u is the displacement of point B with respect to point A or relative to point A. So if point A is going to move, we're going to have to add it algebraically in order to find the absolute displacement of point B. So coming back to this example problem, we can easily calculate the displacement of point B simply by considering segment 1. Point A is fixed, right? And therefore, the displacement arising from segment number 1 is going to be the displacement of point B. But when you go to point C, we're going to have to consider the movement of point B as well, right? But the point B could be moving to the right or moving to the left, depending on the problem. Then the movement of point C is going to depend on that, right? Either we're going to have to subtract the movement of point B or add the movement of point B in order to get the movement of point C from the displacement of segment number 2. So we need a sign convention here. So let's say the displacement due to a tensile force is positive, alright? In other words, extensions are positive, compressions are negative. So here are the equations for calculating the displacements of these key points B, C, and D. Displacement of point B is simply equal to the deformation of the segment AB, which is NAB times LAB divided by EAB times AAB. Displacement of point C is the deformation of AB plus deformation of BC. So we get this. And displacement of point D is going to come from the deformation of all three segments. So we get this long equation for that. Remember, we are using a sign convention, right? And therefore, some of these terms could be negative. So that's it. So this is how you calculate the displacement at a point on a rod with multiple segments.